Starting with our chapter Electrochemistry of Physical Chemistry, second semester. First, we will study section A, that is electrical transport. So, what is electrical transport? First of all, we'll study with this topic, and in this topic, we'll study electrolytic and metallic conduction. Substances which allow electricity to pass through them are known as conductors, whereas substances which do not allow electricity to pass through are known as insulators. Conductors are divided into two classes: those which conduct electricity without undergoing any decomposition, these are called electronic conductors, and those which undergo decomposition when a current is passed through their aqueous solution is known as electrolytic conductors or electrolytes, that is solution of acids, bases and salts in water, fused salts. In this case, the flow of electricity is due to the movement of ions. Electrolytes are further classified into two main categories as strong and weak. Strong electrolytes are substances like strong acids जैसे HCl, HNO3, H2SO4 and strong bases, that is NaOH, KOH and most of the inorganic salts. They dissociate almost completely in the aqueous solution or in the molten state and hence conduct electricity to a large extent. Weak electrolytes are substances like weak acids जैसे acetic acid, HCN, H2CO3, H3PO4 and weak acids. Weak bases, this is NH4OH, calcium hydroxide, aluminum hydroxide. These have low degree of dissociation and hence conduct electricity to a small extent. Substances like sugar, urea, etc., the solutions of which do not conduct electricity are known as non-electrolytes. Factors affecting electrolytic conduction. First factor is intra-ionic attractions, which depend upon the interactions between the ions of the solute and hence are called solute-solute interactions. On the basis of substances are classified as strong electrolytes and weak electrolytes as already mentioned. Second factor is the solvation of ions, which depend upon the interactions between the ions of solute and the molecules of the solvent and hence are called solute-solvent interactions. Third factor is viscosity of the solvent, which depends upon the solvent-solvent interactions. The effect of all these factors decreases with increase of temperature, hence the electrolytic conduction increases with increase of temperature. On the other hand, the electrical conduction of electronic conductors decreases with increase of temperature. Alternatively, the factors on which electrolytic conduction depends are as follows. First is nature of electrolyte, that is strong electrolytes ionize completely in the aqueous solution and hence conduct electricity to a large extent, whereas weak electrolytes ionize to a small extent and hence conduct electricity only to a small extent. Second is the nature of ions, nature of the solvent, that is electrolytes ionize more in a second factor is the nature of solvent, that is electrolytes ionize more in a polar solvent, hence greater is the polarity of solvent, greater is the ionization and hence greater is the conduction. Third is concentration of the solution, higher the concentration of the solution, less is the conduction. This is because in a weak electrolyte the ionization is less, whereas in a strong electrolyte the inter-ionic attractions are high at higher concentrations. With dilution, inter-ionic attractions decreases and hence conduction increases. Temperature, on increasing the temperature, dissociation increases and hence the conduction increases. Difference between metallic conductors and electrolytic conductors. Main point of differences between these are: number one, between metallic conductors, flow of electricity takes place without the decomposition of substance. Flow of electricity is due to the flow of electrons only, there is no flow of matter. The conductance depends upon structure and density of the metal and the number of valence electrons per atom. Third is the electrical conduction decreases with increase of temperature. This is because kernel starts vibrating, which produces hindrance in the flow of currents. flow of electrons. The resistance offered by metal is also due to vibrating kernels. Then is the case of electrolytic conductors. Here flow of electricity takes place accompanied by the decomposition of substance, that is electrolyte. Second is the flow of electricity is due to the movement of ions, and hence there is a flow of matter. The electrical conduction increases with increase of temperature. This is generally due to increase in dissociation or decrease in the inter-ionic interactions. Fourth is the resistance shown by an electrolytic solution is due to the factors like inter-ionic attractions, viscosity of the solvent. Then we'll come to the electrical resistance and conductance. Every substance offers resistance to the flow of electricity to a small or a large extent. The law that gives the exact value of resistance is known as Ohm's law. It states that in addition to metals, graphite and certain minerals also conduct electricity due to the presence of free electrons in them. Hence, they are collectively called as electronic conductors. If to the ends is equal to kg meter square upon second cube into a square, it is seen that like metallic conductors, solutions of all electrolytes also obey Ohm's law. It is obvious that a substance which offers greater resistance will also less electricity to flow through it. This result also follows from Ohm's law, according to which I proportional to 1 upon R. The reciprocal of the electrical resistance is called the conductance. It is usually represented by C. The C is equal to 1 upon R. It is a common practice to speak of the conductance of a solution rather than its resistance. Units. The unit of conductance are Siemens or reciprocal ohms, written as ohm inverse or mho or rho. 1 Siemens is equal to 1 ohm inverse. For example, if a solution has a resistance of 10 ohms, it is said to have a conductance of 1 by 10 ohm inverse, or 1 by 10 mohs, or 1 by 10 ohm inverse, 1 by 10 Siemens. Now coming on to our next section, that is specific, equivalent and molar conductivities. So specific conductivity, or simply called conductivity, it is observed that resistance R of a conductor is directly proportional to its length of the conductor and inversely proportional to its area of cross section, that is R proportional to L upon A, or R is equal to rho L upon A, where rho is a constant of proportionality called specific resistance or resistivity. Its value depends upon the material of the conductor. The reciprocal of resistivity is known as specific conductivity or simply conductivity. It is denoted by kappa. Thus, if kappa is the specific conductivity and C is the conductance of the solution, then R is equal to 1 upon C and resistivity is equal to 1 upon specific conductivity. So 1 upon conductance is equal to 1 upon kappa into L upon A. So kappa is equal to conductance into L upon A. This L upon A is called cell constant. Now if L is equal to 1 centimeter and area is equal to 1 square centimeter, then kappa is equal to conductance. Hence specific conductivity of a solution is defined as the conductance of a solution of 1 centimeter length and having 1 square centimeter as the area of cross section. Alternatively, it may be defined as the conductance of 1 centimeter cube of the solution of electrolyte, or in terms of SI base units, it is defined as the conductance of 1 meter cube of the conductance. If V is the volume in V centimeter cube, the specific conductivity of such a solution at this volume and dilution V is written as kV. Similarly, at a concentration C, it is represented as Kc. Now, coming on to resistivity in its units. So, rho is equal to Ra upon L is equal to ohm centimeter square upon centimeter is equal to ohm centimeter or ohm meter in SI units. 1 ohm meter is equal to 100 ohm centimeter. Specific conductivity kappa is equal to 1 upon resistivity is equal to 1 upon ohm centimeter is equal to ohm inverse centimeter inverse or Siemens centimeter inverse or Siemens meter inverse in terms of SI units. So 1 Siemens centimeter inverse is equal to 100 Siemens meter inverse. Now coming on to the equivalent conductivity. For comparing the conductances of the solutions of different electrolytes, it is essential that the volume of solutions should be same and they must contain such definite amounts of electrolytes which give ions carrying the same total charge. The best choice is therefore to consider the solutions having equal volumes and containing their corresponding gram equivalent weights. Conductance of such a solution is called its equivalent conductivity. Hence, equivalent conductivity of a solution at a dilution V is defined as the conductance of all the ions produced from 1 gram equivalent of the electrolyte dissolved in V centimeter cube of solution when the distance between the electrodes is 1 centimeter and the area of electrodes is so large that whole of the electrolytic solution is contained between them. It is represented by lambda equivalent. Now consider relationship between equivalent conductivity and specific conductivity. The equivalent conductivity of a solution is usually not found directly but is calculated from the specific conductivity. The relationship between equivalent and specific conductivity may be obtained as follows. Consider a rectangular vessel with its two opposite walls on 1 centimeter apart and made of some metal or steel sheet so that these acts as the electrodes. Now consider case 1. Suppose 1 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is taken in the vessel. The conductance of the solution will be then taken to be its specific conductivity. Further, if 1 centimeter cube of the solution taken contains 1 gram equivalent of the electrolyte, the conductance of the solution will be its equivalent conductivity by definition. Thus, when 1 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is considered, the equivalent conductivity is equal to its specific conductivity. Now consider case 4th. Suppose 4 centimeter cube of the solution containing 1 gram equivalent of the electrolyte is taken. Conductance of the solution will be still equal to its equivalent conductivity at this dilution, but now there will be 4 cubes each of volume 1 centimeter cube. The conductance of each 1 centimeter cube of the solution is equal to its specific conductivity, so that the total conductance of the solution is equivalent conductivity is 4 times the specific conductivity. In general, if the volume of the solution containing 1 gram equivalent of the electrolyte is V centimeter cube, we have equivalent conductivity is equal to specific conductivity into volume V. So lambda equivalent is equal to K V into V. In terms of concentration, if the solution has a concentration of C gram equivalents per liter, that is C gram equivalents represent in 1000 centimeter cube of the solution, then the volume of solution containing 1 gram equivalent will be 1000 by C. Hence the above expression may be written as lambda equivalent is equal to Kc into 1000 upon C equivalent is equal to Kc into 1000 upon normality. Note carefully that in the above expression, V is the volume of solution in centimeter cube containing 1 gram equivalent of the electrolyte and C is the concentration in grams equivalent per liter. So lambda equivalent is equal to K into V is equal to ohm inverse into centimeter cube upon gram equivalents. So ohm inverse centimeter square gram equivalent inverse is equal to ohm inverse centimeter square equivalent inverse is equal to Simon centimeter square equivalent inverse or Simon meter square equivalent inverse in case of SI units. 1 Simon meter square equivalent inverse is equal to 10 to the power 4 Simon centimeter square equivalent inverse. Molar conductivity of a solution is defined in a similar manner to that of equivalent conductivity, as molar conductivity of a solution at a dilution V is the conductance of all the ions produced from 1 mole of the electrolyte dissolves in V centimeter cube of the solution when the electrodes are 1 centimeter apart and the area of electrodes is so large that the whole of the solution is contained between them. It is usually represented by lambda m. Relationship between molar and specific conductivity. As in the case of equivalent conductivity, the molar conductivity is related to the specific conductivity as follows. Lambda m is equal to Kb into V. Lambda m is equal to Kc into 1000 upon C is equal to Kc into 1000 upon molarity. Thank you so much.